lecture we were discussing about a simulated potential flow by past a circular cylinder by considering a uniform flow and a doublet superimposed together. We will continue with that. We tried to get a sketch of the streamlines around the body. Now we will calculate the pressure distribution around the body. So to calculate the pressure distribution, so pressure distribution on the what we will calculate is pressure distribution on the surface of the cylinder, and this is very critical, you know why. As per the theory of boundary layer, pressure distribution outside the boundary layer is imposed on the fluid on the boundary layer itself. So if you calculate a pressure distribution from potential flow consideration, that pressure distribution can be considered to be valid on a fluid where boundary layer assumptions are justified, even for a case when viscous effects are present. So although the pressure distribution is calculated based on potential flow. So this is one of the big applications of potential flow. Of course you can use that potential pressure distribution up to an extent till you have boundary layer separation. If you have boundary layer separation, you cannot use that. So assuming, so first of all it is a potential flow, and if density is constant and if there is no great difference in elevation, then you have P plus half rho u square, or rather V square, is equal to constant, right. So what are the assumptions behind this? Steady flow and constant density flow, irrotational flow, okay. So with these considerations you can write that and there is no negligible change in potential energy. So with this P plus half rho V square equal to constant. So you can write whatever is coming from infinity, first stream, this is P infinity. So P infinity plus half rho u infinity square is equal to P plus half rho V r square plus V theta square, because resultant V square is V r square plus V theta square. So this P we are calculating where? On the surface of the cylinder, that means small r equal to capital R. So P infinity plus half rho u infinity square is equal to P plus half rho V r at the surface of the cylinder, we are calculating this at the surface of the cylinder, V r is 0 and V theta is minus 2 u infinity sin theta. So this is 4 u infinity square sin square theta. So in fluid mechanics, a non-dimensional pressure is defined as coefficient of pressure Cp is equal to, this is called coefficient of pressure, P minus P infinity by half rho u infinity square. So this is 1 minus 4 sin square theta as per the potential flow theory. So if you calculate it, so you start theta equal to 0 from here, and then if you make a sketch of Cp versus theta, you get something very interesting if you compare it with a practical experimental situation. So, Cp versus theta. So, see at, so this is, let us say this is pi by 2 and this is pi. So, when, so let us say this half cycle is of our interest. So, when theta equal to 0, Cp is 1. When theta is equal to pi by 2, it is 1 minus 4, that is minus 3. So, 1, 2, 3, this is minus 3. So, this point, and when it is pi, it is again 1, this point. So, through these 3 points, if we draw a sinusoidal curve, it is something like this. Okay. So, now what is the practical situation? The practical situation will be, let us compare this with a practical situation of Reynolds number 10 to the power 5. Reynolds number 10 to the power 5 means rho u infinity into 2r by mu, the viscosity of the fluid. Let us say that is 10 to the power 5. So, you will see that up to a limit which is very close to pi by 2, it will follow this trend, and then this will be like a constant. So, this is Reynolds number equal to 10 to the power 5. The reason is that there is a boundary layer separation at this point, after which there is a wake where you have almost a constant pressure distribution. So, up to this you can see very faithfully till the boundary layer has separated, very faithfully you have the pressure distribution reproduced by the potential flow theory solution. So, it is not that the potential flow theory is absolutely hypothetical and it has no relationship with the physical reality. Okay. So, we have seen how to model flow past a circular cylinder, but if you calculate a drag force on the cylinder, which is a matter of great engineering importance, because of the symmetry of flow, purely because of symmetry of flow, you can see that the drag force will be 0, right. So, whatever is the pressure distribution from this side, the same will be the pressure distribution from this side. So, the horizontal components will cancel and that will make the drag force equal to 0. But in reality, if you subject a cylinder to a flow, then there will be a drag force, and it is very important to pinpoint what is that drag force. So, to get into that, we have to introduce something, some feature in addition to the uniform flow and the doublet, to introduce the drag force on a cylinder. So, that particular thing is nothing but a viscous effect. So, when this viscous effect was not considered in the analysis, it was considered to be a paradox, and that was called as D'Alembert's paradox, that although there is a fluid, there is a solid body, but net drag force is 0. This theoretical calculation which gives 0 drag force is not because of any paradox, but because of the fact that viscous effects are not considered here. When viscous effects are considered from the Cp versus theta real graph which I had just drawn, you can clearly see that the pressure distribution on this side is different from the pressure distribution on this side, and that will give rise to an asymmetry. What about lift force? So, what is drag and lift, just to recapitulate? So, if you have a body of any arbitrary shape, if you have the resultant force, that resultant force you can decompose into two parts. One is along the direction of flow and another is perpendicular to the direction of flow. In the plane you can resolve it into these two components. If it is a 3-dimensional flow, you can also have a lateral thrust component, and these components are very important because all the aerodynamic situations, that is how aircrafts fly and all, these depend on a significant control over the lift and the drag force. So, and also the lateral side force. So, this is called as the drag force and this is called the lift force. So, the without viscous effect we cannot generate a drag force in this case, because symmetry in the pressure distribution cannot be broken. The next golden question is, without viscous force can we generate a lift force? We have understood that without viscous force we cannot generate a drag force, but without viscous force can we generate a lift force? So, to examine that, one can refer to a very common practical experiment. Practical experiment is, let us say you have a tennis ball or a cricket ball like this. So, in a fluid where viscous effects are even negligible, if you make this cylinder or a sphere for a ball, you may approximate it as a sphere. If you spin it in this way, then you will find that there is a tendency of it to go up or down depending on the direction of the spin, and this is the so called top spin in a sports ball, and this is due to an effect called as Magnus effect. So, what is this effect which can give rise to a lift force where everything is absolutely symmetric? So, intuitively we do not expect a lift force. In fact, in this case you do not get a lift force, because again just like the drag forces from the two sides have cancelled, lift forces from the bottom and the top will also cancel. But if you bring in a rotation, rotation can break the symmetry, not for the drag force but for the lift force. So, rotation in the paradigm of a potential flow is something which is what type of vortex? We have discussed this in kinematics. This is a irrotational vortex or a free vortex. So, we will consider a rotation, and to bring in a rotation the natural choice is a particular type of flow which is a free vortex flow. We cannot bring force vortex in the picture here because that is not an irrotational flow. We are talking about irrotational flow here. So, we will next study, our next example is vortex, and this, although we say vortex, this is irrotational vortex, we have to specify this very clearly, or free vortex. So, how is a free vortex defined? Free vortex is defined as V theta equal to C by R and VR equal to 0. So, question is that what is the complex potential corresponding to this? That is the question, because we have to basically superimpose this with the uniform flow plus doublet to give a rotation to the circular cylinder. So, you have df dz is Vr minus I V theta into e to the power minus I theta, right. So, minus I C by R e to the power I theta, right. So, minus I C by Z, right. So, F the complex potential you can find out by integrating this with respect to Z. So, F is minus I C ln Z, right. Now, this C is an arbitrary constant, we should relate it with the strength of the rotation, which is the so called circulation. So, the circulation is defined as follows. How do you define this circulation? You define this circulation as the cyclic integral of, or a contour integral rather, contour integral of V dot dl over a closed path. So, this is nothing but V theta into R d theta from theta equal to 0 to theta equal to 2 pi, dl is R d theta. So, V theta is C by R and these two get cancelled, that is how you can get rid of the singularity. So, this will be C into 2 pi, therefore, C is gamma by 2 pi. So, this you can write minus I gamma by 2 pi z, and this will become minus I gamma by 2 pi ln of z. Okay. So, when gamma is positive, what kind of circulation it does indicate, clockwise or anti-clockwise? When gamma is positive, it indicates clockwise, anti-clockwise rotation. Therefore, this minus sign, if it is there finally, that is if it is negative it shows anti-clockwise rotation, and if it is positive it shows clockwise rotation. Okay. So, this we have to keep in mind because we have to physically interpret some of the results. Okay. So, now we will come to this question. What is the superposition of uniform flow plus doublet plus vortex? What is this? So, uniform flow plus doublet is physically representative of a flow past a circular cylinder when the cylinder is not rotating, and this adds a rotation to the cylinder. Okay. So, this physically mimics flow past a rotating, so potential flow past a rotating circular cylinder. Okay. So, in this case what is F? Uniform flow along x axis is u infinity z plus doublet plus vortex this M you have already seen that it is u infinity into r square to represent the flow past a circular cylinder of radius r. Now, with the introduction of this, with up to this we had already ensured that there is no penetration boundary condition at the surface of the cylinder. With the introduction of this, that is no more assured. So, we can assure this by adding a constant, say A plus IB to the expression of the complex potential, because in that case we can choose A and B as per our freedom. This is just a constant, so it will not reflect in terms of velocity, it will just alter the values of the stream function and velocity potential, but not their derivatives, because these are constants and velocities are derivatives of stream function and velocity potential. So, this will not alter the velocity, but it will allow us to adjust the velocity in such a way that the radial component of velocity is 0 on the surface of the body. Okay. So, how do you do that? First of all, let us write this u infinity z is r e to the power I theta plus u infinity r square by r e to the power minus I theta minus I gamma by 2 pi ln r minus I gamma by 2 pi ln e to the power I theta is I theta. So, I into I will be minus 1 into minus will be plus 1 plus gamma by 2 pi theta plus A plus IB. So, you can separate the real and imaginary parts, u infinity r plus u infinity r square by r plus gamma by, so this into cos theta plus gamma by 2 pi theta, this is the plus A, that is the real part, right. Gamma by 2 pi, yes. An imaginary part u infinity r sin theta plus u infinity r square by small r, this into minus sin theta minus gamma by 2 pi ln r plus b, right. So, this is phi, this is psi, right. So, to set up a no penetration boundary condition with a reference streamline on the surface of the cylinder, you must have psi equal to 0 at small r equal to capital R. Okay. So, psi equal to 0 at small r equal to capital R means u infinity r minus u infinity r sin theta. You know, this part was already 0 with uniform flow plus doublet minus gamma by 2 pi ln r plus b is equal to 0. So, you can set b is equal to gamma by 2 pi ln of r. Okay. So, in this way you can model this with a particular choice of B, an arbitrary choice of A also you can make a choice of A arbitrarily, because although you have a constraint on stream function, you do not have a constraint on velocity potential reference. Okay. Constraint on stream function is also up to you. I mean, you may choose of course a non-zero stream function on the surface of a body, there is nothing wrong with it, but customarily we choose it as 0, that brings into that extra constraint. So, potential flow past a rotating circular cylinder can be represented by this generic thing. Of course, a matter of interest, primary interest is to see what is the velocity field out of this, but a matter of more intense primary interest is to see what is the lift force and the drag force, because that is what is a matter of engineering concern, and that lift force and drag force we can calculate using a very powerful theorem called as Blasius force theorem, which can even take a body of any arbitrary shape, so long as the body has a closed contour. And in the next lecture we will see that how to find out the lift and drag force on an arbitrary shaped body given you have the complex potential using that Blasius force theorem. Thank you very much.